Hello everyone, and welcome again to this class. And as you remember that we were doing an example on this variational calculus, using the variational calculus and implying the Hamilton's least action principle, which gives you the integral or line integral or action integral between the 2 points of a path followed by a body in configuration space is going to be extremum or minimum, and for that functional which is defining the path of that motion of that body is going to follow the Euler-Lagrange equation. So we have done two example, that is, one was shorter distance between the 2 points on a plane, and shorter distance between, that was a straight line, and the shorter distance between the 2 point on the sphere, that was going to be the curve of the great circle, that is by cutting the circle by a plane which is passing through the origin of that sphere. That could be infinite number of that. So now let's move to another example, that is the minimum surface of revolution. So that means if you consider this, you have to consider the surface generated by revolving a line connecting two fixed points. So if I have a 2 point, that is, let's say this is x1 y1 and this is x2 y2 in the plane, and you draw a certain curve from between these 2 points, okay, certain curve, and then if you rotate this curve along any axis, okay, either x-axis or a y-axis, so what is the minimum surface area this particular curve is going to approach, depending upon the minimum criteria of line integral, that we had to find it. So suppose you have a surface, we have a surface xy, and then the 2 points are there, and if you draw a curve between 2 points, as you can see here, this is my curve between these 2 points, and if I rotate this curve along the y-axis, then what is going to be the nature of that surface? Okay, so for that, what we need is that the area of that, I have to find the area. So if I find the strip area element of that and then integrate over between the initial to this final, then I'm going to get the minimum, and applying this least action principle. So this area is going to give me, so what is this radius at this particular position, okay, whatever you take, this position, so, and then the perimeter of this circle that is there, that is twice pi. This is, in this case, this is because this is along the x-axis, so this is going to be x, twice pi x, and what is the thickness you are taking, that is going to be my dx square plus dy square. So this is my area, that is twice pi x dx, and ds, we know that is dx square plus dy square under root. So then I can take dx common, and dx will come out, and I have 1 plus y dot square. So this is twice pi x, 1 plus y dot square. This is my so if I integrate it between these 2 points for the line integral, so the area is total area is this integral. So now you can see that this is my functional, okay, f in this case, my functional is y dot and x. So for this integral to be minimum, what I want that the functional, which is x1 plus y dot square, it must follow this Euler-Lagrange equation, okay. So that means now because this is df by dy, x is independent coordinates, but in my functional there is no y, okay. So this part is going to be 0, so naturally this is going to be the constant of motion. So let's put it equal to alpha. So df by dy is my alpha, which is going to be the constant. Now try to find this df by dy dot, this is which is going to be constant. So y dot is here, so I can have this x here, and then similarly you have half 1 plus y dot square, and minus, this is going to be half minus 1, this is going to minus half, and then you differentiate this is going to be twice y dot. So twice will cancel out, so what you're going to have, x y dot, So you have x y dot, and then this is minus 1 upon under root 1 plus y dot square. This is 1 plus y dot square, and this is going to be constant alpha, because this is this df by dy is 0. So now you cross multiply and the square everything. So what you get, this is x square y dot square, and this is alpha square, and then u square. This becomes 1 plus y dot square. So this is, if you cross multiply this with alpha 1 and then alpha square y dot square, and you take y dot square one side, and then this is x square minus alpha square alpha. So you have dy by dx is alpha divided by underscore x square minus y square. This is quite straightforward integration, the standard integration. When you integrate over dy, so this is going to be integration dy, and then you have alpha common, so and then the dx is there, and then whole x square minus y square, and then a constant of integration which is beta. So this is standard integration. This is cos hyperbolic x by a plus some beta. So where alpha and beta, where the constant here are determined by requiring the curve to pass through these two endpoints. So this is this also can be written as this in terms of x, because I have y is equal to alpha. So I taken y minus beta. I can write y minus beta here, and this is a cos hyperbolic inverse x by a. So I can take the inverse of that. So this becomes or this a can be along this side also. So y by beta by a. So then not a cos hyperbolic. This is cos. This is going to be the cos hyperbolic of y minus beta by a. This one, and this is going to be x by a. So x equal to a times alpha times, basically this is alpha times y minus beta y cos hyperbolic, and this is the equation of a catenary. That is, catenary is a shape that if you hang something with its 2 points, then under the action of the gravity, always it is going to hang like this. Okay, whether it is a chain or rope and whatever it is, like whatever the gravity is acting on this, that this is the form of the catenary. So when you have 2 points on a surface, and then you draw a certain curve on that surface, and then you rotate along axis, then the minimum surface it is going to follow, it is that is because of the catenary curve. Okay, so because if you see, like if you see that if you have a straight, like a very tight rope here between 2 points, and then if you rotate this, we're going to have a cylinder. Okay, but this is not very rigid, and then it can hang around it. So when you rotate it, so this somewhere it will go down, somewhere go up. That because of what's the gravity, how the gravity is acting on it, and then according to that curve between the 2 points is going to have the minimum surface of evolution. One important thing is to mention that during the calculation, what should we care that, for example, if we say if I have 2 points x1, y1 and y2, the same equation, and this is given by the function ys, such that if we revolve this along the x-axis, this has been asked, if you revolve around the x-axis, find the surface of minimum revolution. So now this is given, and you choose this x-axis and this is y-axis. Okay, now what is the area? Because the area, this is twice pi, ds is okay, and this is going to be my y. Okay, this is going to be my y. So this is my y. So see what is the difference here. So in this calculation, here I have x because this distance is along x-axis. Now see the problem. Now I can take y, and this is 1 plus y dot square. So my equation is, earlier my function was twice pi x 1 plus y dot square. Okay, now my functional is in this case is twice by y 1 plus y dot square. So now this depends upon y. Okay, earlier my del f by del y was 0. Now my del f by del y is not 0. This is going to be twice pi. This is going to be 1 plus y dot square. Okay, so twice pi if you take common, and then df by dy is y dot 1 plus y dot square. So if you put it into this equation, into this Euler-Lagrange equation, what you're going to get is this. So earlier what you were getting, that dx of x y dot 1 plus y dot square was a constant, and that was very easy to solve. That was straightforward. Okay, quaternary problem. Here also, if you solve this equation, that is going to give you the same result, but you see that this is going to be very complicated. So what I'm trying to say, that this equation not appear to be simple. So what you must do, that while you are creating your problem to solve, creating your visualization to solve that, you try to choose the axis such that, for example, in this case, if you would have chosen this as y-axis, if you have chosen as this y-axis and this as x-axis, so this is curve, if you revolve the curve around x-axis, okay, so what will happen? So this becomes your x, okay. So you see the same problem you're going to give there. So your x and y2 prime is there, and you revolving around this x-axis. So now you have chosen this x-axis, revolving around this x-axis, these 2 points. Okay, revolving around these 2 axes. So now your functional has to be like x 1 plus y dot square. Then the solution will be simple. So whenever you're doing the problems, try to use it's going to be through the experience, that not automatically you're not going to get it, but this is just to give you a flavor that choosing a different kind of axis is going to complicate to solve the problem also. Okay. So now let's quickly move to what I want to say, that simply think before choosing the right system, so that we do not face such difficult situations. And let's move to the new example, which is the Brackett-Crone problem, which is had to find the minimum if you have 2 points, and if you release a marble between 2 points, these 2 points from x to the y axis. So if you release a marble at this position, so this marble to come from position A to position B, what should be the path of the marble so that the time taken is going to be minimum? This is the Brackett-Crone problem. This was very interesting problem, and normally you think what is going to be the less time, like along the straight line. It is not going to be the straight line, it is going to be the geodesic, is going to be some other cycloid equations. So it can have like, you can think it's going to state there's going to have less time, it's going to have this path, this path, this path, or whatever the between this path. So this, what is the actual path this marble must follow, so that reaching from this position to this position, it is going to have less time. Okay, so let's try to do quickly. So this is what we had to see. So first thing that we are talking about minimizing the time. So in all other we were minimizing the path, that was we were doing ds here. Now we are minimizing the path, that is going to be dt here from 0 to time t, and that can be dt can be is s divided by v, going from point A to B. Now ds, we know that this is 1 plus y dot square and going to be dx. Okay, and from the conservation of energy, because it is falling and the kinetic energy, potential energy changing into the kinetic energy, I can have this half mv square is mgy, because this is y, and then from here we can find we need to find v, so this is going to be under root twice gy. So using relation 1, what I can do is I can put this relation into this is my ds, so I can put ds is 1 plus y dot square, and this in place of v you put this your 2gy, and then dx is there. Okay, so because 2g is constant, so I can take under root 2g outside of the integral, and then now this is my function. This is my function. I want to minimize this. Okay, so for minimizing this function has to follow this Lagrange equation, and my function is fy and y dot. So now this function is not depending upon, only depending upon y, it is not depending upon x, over which I am going to differentiate. So what is the problem here? So then in such situation, like a problem is you see this problem arises because if I would have chosen this as the x-axis, this as an x-axis, and this as a y-axis, so this problem would not have been there. So but because I have chosen this as a y-axis, so this you see the problem is, so I'm not getting this d by dx. So for that I have to use the Beltrami identity, that for this Beltrami identity says that this is going to be minus y dot delta f by delta y dot equal to c. Okay. So I'm going to use this thing. So if my function is not depending upon this independent coordinates, so I'm going to use a Beltrami identity, so which becomes which solve everything in terms of this y dot, because y dot because y dot is not, we have already defined this is my dy by dx, so that's why it is y dot. So now let's apply the above this identity and solve it, because f is my this thing. If f is this is 1 plus y dot square y, so and then y dot is here, and what is df by dy, dy of this f, I can have this, you can equate this as this is say delta y dot of 1 plus y dot square by y. So because I can take under root y outside, this is going to be delta y dot 1 plus y dot square, because 1 by y is not going to contribute here. So this is nothing but going to be 1 by under root y, and this is simply 1 by 2 1 plus y dot square into twice y dot. So 2 will cancel out, so 2 this is twice y dot, so 2 will cancel out, and you have this is same as this 1 by y as I have calculated here is outside. So this y dot and earlier y dot becomes y dot square, and then you have 1 plus y dot square equal to constant. So now open this. Okay, so what you're going to get is like under root y, you take under root y common from here, this is so you write it like 1 plus y dot square divided by y. So this y you can call common, and then it goes to with c square root y, and then you square all these things. So this is by cross multiplication, so this is 1 plus y dot square and then you have c under root y dot square. So this is simple calculations, and then finally you get dy, and then you have dx here. Now you have dx, and then because all these functions depending upon y, so you are integrating here with respect to y, and then other side you have dx. So this is going to be x plus some constant of integration, and y and c1 minus y is going to be your dy. So now to integrate this, let us put this y equal to c1 sin square theta, and this dy is twice c1 sin theta cos theta and d theta, this is we know. So I have x plus c2 equal to y c1 minus y. I have this is y c1 minus y, this you have dy. So y I put this is c1 sin square theta, and c1 and this c1 sin square theta, and d theta is this dy is here twice c1 sin theta and d theta 2 theta. So x plus c2 is here, so twice c1 will be here. So I can you can do this very quickly, because this is c1 this is sin squared theta, and then you can see take common, this is 1 minus sin squared theta and side root, so this will cancel out. So you're going to have sine squared theta, and this is 1 cos squared theta. This is going to be the cos squared theta. Okay, so and then this is going to be tan squared theta, or this you take outside, this is going to be sine theta by cos theta, and then you have sine theta cos theta. So this cos theta will cancel out. You have sine this sine from here, because this is under root, you get sine theta by cos theta. This is sine squared theta d theta. Okay, so now sine squared theta 1 minus cos theta, you integrate it here. So what equation you are going to get is x is like your c1 theta minus half sine 2 theta, and then this c2 is here, and then because you define y is c1 sine squared theta, so I have c1 by 2, this is 1 minus cos 2 theta. So these c1 and c2 are to be behind from the condition, from the boundary conditions. So these are the equation of cycloid. So because if you compare the cycloid standard equations are x, you see x, you have x here, and then you have theta, and then sine theta, you have theta and then sine theta, everything x is constant. Similarly for y, you have y here, and then this is r, this is 1 minus cos theta, you have 1, this is constant r, and this is cos theta. So this is exactly giving you the parametric equation of a cycloid. Okay, so that means if a barbell is rolling from point A to point B, one position to another position, under the action of the gravity, so the minimum time it is going to take to the path which is a cycloid. Okay, now what is a cycloid? A cycloid is like this path. That means if you cycloid is like if you have a circle, and if you follow the point of this circle on this, then this is going to be the cycloid. Okay, so this is what you have a cycloid, and then you can find these equations. I'm not going to define all these things, equations. So okay, so and then this is your x is equal to r theta minus sine theta, and y equal to your r 1 minus I think cos theta. This is what I'm going to have is r theta minus sine theta, r 1 minus cos theta. Okay, so this is my equation. So you can find this equation as from the cycloid, because like if you have a cycloid here, and then you get some position here of this circle, this is the point where you wanted to find your position. This is going to be given by x and y. So you have my x here, and this is the radius r, and this is also the radius, and this is going to be so what is this thing? So this is x is this, and this constant, so this is say a, so this is say a, so this is you have x plus a equal to what? So this is x plus a is nothing but this is equal to this arc. Okay, and this arc is radius times the theta measured by this angle. So this is, if this is my theta, so this is going to be r times theta. So now you can write as x is equal to r theta minus a. This is my one equation, and then for y coordinate I can write this, y coordinate I can write this. Y is this thing. So one part of this is your r, so this is r, and say this is my b, so r plus b. So y is equal to r plus b. And what is this a and b? What is this a and b? So a and b you can find out like here from here, that is this is a and this is b. So if you see that this angle is theta, so this angle is going to be theta minus pi by 2, because this angle is pi by 2. Okay, so for theta is, this angle is going to be theta minus pi by 2, and this is your r. So if you write a equal to this, a is equal to this is going to be cos r cos theta minus pi by 2. So this is going to be a, this is going to be r cos theta minus pi by 2 is sine theta. So if you put it here, is this is r theta minus a is r sine theta. So if you take r constant, this is theta minus sine theta. This is your r minus theta, and this b is basically r sine theta minus pi by 2. So this is going to be minus r cos theta. So if you put in b, this is y is equal to r plus b. So this is r minus r cos theta. So this is r. If you take r common, this is going to be 1 minus cos theta. So this is what the cycloid is. That is, if you follow the point, the path. So this marble is going to follow the path of a cycloid, in which when it is going from one point to another point, it is going to have the minimum time. This particular special problem is known as the Brachistron problem, and this was a very interesting problem to be solved. And I think you actually get the flavor for this. So now I stop this. So today we do two more example based on the variational calculus. One is for minimum surface of revolution, and the second is the Brachistron problem, where you get that how to find the minimum curve for the time variations. Okay, and for this you see that is what I have here in this case. So when actually you think that, like, when straight line is going to have the minimum time, naturally you are going to think that, because this is the shortest distance between these 2 points, and this marble, if marble is flowing, it is going to have the more time. So but you see that the effect of the gravity is here, and you can have this. Okay, so one more thing I wanted to mention, that like when would I have been chooses that x axis along this axis, the life would have become very easy, because like in this case I have chosen this x axis and this is my y axis, and the marble comes down and goes to this position, then you see that my v is not twice gy, as in earlier case, that is twice gy, or is twice gx. And now, so my equation becomes more simpler. That is earlier it was 1 minus y dot square by y under root. Now this is now x here in place of my y, and so this is my functional, and then you have del f by del y minus d dx, and delta f my delta y dot, so equal to 0. Now my previous case x was not there, so I had to use the Beltrami identity. Now I have x dependence here, and which is very quite easy. So and df by dy is going to be 0. So then you can solve quite easily the equation, and you can see that. And in the next lecture I'll try to give you the flavor that how getting this x into my functional is going to ease the calculations. So I'll stop this at this position, and we'll meet in the next lecture with this continuing this problem of the Brachistron. Thank you very much.